So as I was saying at the beginning, so I changed a bit the schedule. So I prefer to do one exercise session less and one theory session more, because we are going to cover two topics that are huge. So that is the early universe part, and tomorrow morning the late universe part. Okay, to show you how to make inference on H0 with gravitational waves. So this afternoon we will not make exercise, okay? Because I want to prepare the ground for tomorrow exercise that is also quite complete, because you must have an understanding of the sources in order to simulate them. So I try to teach you how to simulate a stochastic background, the data for a stochastic background, and then how to perform parameter estimation for a stochastic background that we have essentially, we will see in this lecture, okay? So I think that we can start, okay? So if there are no questions, so let's start with the summary of the morning, okay? So I think that this slide summarizes what we have done this morning. So we have introduced gravitational waves as gauge invariant degrees of freedom. So we have seen that this guy here propagates in our universe almost freely, okay? When I say almost, I refer to something that also Tanya mentioned before, that are the anisotropies. So the anisotropies of the stochastic background are induced by the fact that these guys propagate in a universe that is not homogeneous nor isotropic, so on smaller scale. Okay, so also the cosmological background feels some anisotropies as photon do. Okay, so I will not cover in this lecture because it's a bit technical. I have some slides if you want, but since we live in a universe where gravitational potential are there and they are not constant, they vary on cosmological scales. So while these waves propagate in our universe, they feel in a similar way as photon does, the photon do. They feel the effects of the gravitational potential, and also gravitational waves are how to say, acquire this directional dependence, right? These are the anisotropies. Of course, the fact that astrophysical sources resides in galaxies, okay, makes this anisotropy larger, because for the intrinsic distribution of the galaxies in our universe. But still, so the famous Sachs-Wolf effect, the integrated Sachs-Wolf effect, so that characterize the anisotropies on larger scale, okay, they are there, both for photons, but also for gravitational waves. And there is a peculiar thing about gravitational waves is that while CMB photons decouple at few electron volts, so very close to us, okay, gravitational waves decouples in the early universe, so they travel more in this varying fluctuation, scalar fluctuation. So in principle, if you compute integrated effects, this should be larger, and that's what happens for gravitational waves. But anyway, since we focus on the monopole, we don't discuss anisotropies, okay? This is the summary. So these guys evolve in our universe. They feel the friction due to the expansion given by this Cal H, okay? So, and if you take the most simple single field Lorentz model of inflation and you compute your tensor power spectrum, okay, the primordial ones, you write it in terms of the tensor to scalar ratio and the amplitudes of the scalar fluctuation. So we know these guys from CMB, okay? This is 10 to minus 9, this is 10 to minus 2, this is 10 to minus 5. This is the quantity of radiation that there is in the universe today, is 5, 10 to minus 5, okay? So, and if you compute this quantity, you realize that this is 2 times 10 to minus 16, okay? So, and if you compare this signal with the noise, or better, the power law sensitivity, that probably Tanya will discuss, that essentially tells you if a stochastic background is detectable or not. So you see that this is well below the sensitivity of current and future generation detectors. So the only hope is here, where we have CMB experiments, okay? Planck in darker green and Lightbird in lighter green, that could have hope to detect this primordial signal for single field Lorentz model of inflation. So, but I think that you already got the point, okay? So here we have no sources, okay? On the other hand, what we want to an extra injection of gravitational waves in order to take this signal and increase at smaller scale. still being consistent with the CMB bound, okay? Because we cannot forget CMB bounds, and we cannot forget stuff that we have here that I didn't report, okay? So, as I was saying at the beginning of this morning, so the easiest, one of the easiest models to increase the gravitational wave background is coupling the inflaton with a gauge field, okay, in an axion inflation model, okay? So here the inflaton is a pseudoscalar axion, okay? You can even relax this assumption and adding a field that is not the inflaton. I will not discuss this. The features will be a bit different. So keep in mind the definition of these parameters that is proportional to the velocity with which this field rolls down along its potential, okay? So the physics is quite easy, okay? Because you have a rolling inflaton that excites electromagnetic quanta of this through this coupling here, okay? So the peculiar thing is that in this kind of models, okay, only one of the two polarization, as we will see here, okay, gets amplified, okay, while the other has a decaying, has no amplification, and it has this tachyonic instability here, okay? A plus is one of the two polarization of the gauge field. So as a consequence, okay, the production of this gauge quanta prolongs inflation, okay, and through this inverse decay constant, this inverse decay mechanism. And the point is that through this coupling between the two gauge field, gravitational waves are sourced up, okay? So in principle, you have the vacuum contribution from gravitational waves, plus you have this extra contribution coming essentially from the gauge quanta, okay? So, and the math is here, okay? You decompose your gauge field in its two helicities, plus and minus, okay? You compute the equation of motion for the gauge field, okay? And then you plug this in a cosmological, in an inflationary setup, okay? And you see again here that there is this constant that is proportional to the velocity of the field. So if you look for this solution, you solve the homogeneous solution, then you solve the full equation with the green function method, okay? And this is what you get, okay? So again, here you see that I am showing only one of the two helicity because it's the one that has this stability. So of course, so if you compute in the same setup the cosmological gravitational waves equation, okay, so you see that it gets sourced. It's what we were looking for, right? So we were looking for an extra source of gravitational waves that is essentially proportional to the derivative or to the divergence of the gauge field, essentially to the electric and magnetic field, okay? Remember that I have to extract the TT part of this guy here in order to be consistent with the left-hand side. But what you notice is that this gauge field becomes seeds for the gravitational waves, okay? And with an even peculiar features, that is that these gravitational waves are chiral, okay? So the fact that these are chiral comes from essentially the fact that we only have A plus that is amplified, okay? And A minus is not amplified, okay? And that's what you will see, okay? So if we go in the chiral basis, so essentially you move from H plus, H cross, and you go in the H left, H right basis, and you compute the power spectrum of the left and the power spectrum of the right modes, you find that this will be different, okay? They will not have the same amplitude. But okay, summing up everything, because at the end of the day, what you do, you sum up the left and right, or the plus and cross, okay? You get a spectrum that you see as a vacuum fluctuation, the usual vacuum that we have computed before, 10 to minus 16, slightly red-tilted, but now there is an extra source of gravitational waves that at some point increase and touch the sensitivity curves of the LISA detector, okay? Here I show for the LISA case, but of course you can do the same exercise for LBK or for ET if you want. But you see now the contribution is coming from two sources, the vacuum contribution and the source contribution, okay? And it's interesting to see that, so we have in a natural way, because this is a very natural model, does not require too much tuning, okay? we have generated an extra injection of gravitational waves at scales that we like interferometer scale. Okay? And if you plug this in a full picture, you see, okay, you see the signal is still consistent with CMB bounds, but at some point it increases, okay? And it touches the sensitivity curves of different detectors, okay? And you see here that we have the vacuum contribution and then the axion inflation contribution. Okay, then you can play a bit. So if you like a bit of Bayesian analysis, okay, you plug this model, you compute the Fisher matrix that we will see tomorrow, and you see which is the precision that LISA, for instance, can measure this kind of signal, approximated like a power law, for different value of the amplitudes and the tilt, okay, and the precision that you would have on the amplitudes and the tilt themselves, okay? So, and you see here that LISA can reach, for reasonable amplitudes like 10 to minus 12, okay, can reach precision of the percent level, okay? And this is a very interesting exercise that goes into the direction to understand what LISA can tell us about the early universe, okay? Okay, so here I just put some more advanced analysis that I will not discuss here, but of course you can approach this kind of models also with the Bayesian tools like the nested sampling or Monte Carlo Markov chain analysis, okay? And what I want to stress instead is this, okay? So you choose some benchmark for your models. So here we are talking about two parameters model, okay, characterized just by an amplitude and the tilt, okay? You simulate your data with this benchmark, then you run your Monte Carlo Markov chain analysis, and you get back some estimate, some confidence interval for the parameters of the model, okay? So for instance, here we are constraining the slow roll parameters in this model, and this constant here that is proportional to the velocity of the inflaton, okay? So, and look at here, so LISA will have the possibility to strongly constrain the parameter space of this model, okay, with very small error, okay? And this is very interesting because we have learned, okay, what I was telling you at the beginning of this model, that we can test fundamental physics with interferometers. In this case, we are testing the axion decay constant, okay, that is related to string theory, if you want, with interferometers, okay? A few years ago, this was not clear at all. We were thinking that all this information could be extracted only from CMB analysis. Then here, this is a recent paper, but a previous analysis in 2016 was one of the first analyses that we did in order to constrain the parameter space for axion inflation model, okay? So, well, this is still inflation, okay? But the situation is the following, okay? So the people were thinking that so you need to add, in order to increase the signal, we need to have this extra injection of gravitational waves coming from adding extra species, for instance, right? Like the inflaton, like the gauge field, okay? Or you can also think about other fields, but okay, what you were requiring to have is a non-zero anisotropic stress, okay, on the right-hand side of the Einstein equation. But instead, people first in the 70s and then in the 90s realized that you don't need in reality to add any extra field, okay, because GR is already helping you to do this job, okay? So whatever I told you up to now, okay, is linear perturbation theory, okay? Whatever you have Einstein equation, you perturb them, even if you perturb at second order, then you vary them and you obtain linear equation of motion. So whatever we discuss up to now, it's at linear order, okay? The equation of motion that I showed you before are at linear order. There is something amazing in GR, okay, that happens, okay? So if you are at linear order, okay, the fact that we live in a isotropic and homogeneous universe allow us to treat separately scalar, vector, and tensor, okay? So if you compute the equation for these guys, they are always decoupled, okay? Scalar evolve by themselves, vector by themselves, and tensor by themselves, okay? They don't talk each other. So what happens at second order in perturbation theory, okay? So, okay, good. So we are very good in doing perturbation calculation, okay? I give you my metric in the Newtonian gauge. For instance, this is one choice. Instead of stopping at linear order, I go to second order, both in the scalar and also in the tensor. So this is a second order tensor, okay? And, okay, taking all this, so I just start computing my Einstein equation, okay? It's a bit tricky, I have to go to second order, but I can do that. So I take my Einstein equation, I compute, I use my projector to extract the TT part, okay? And see what happens. It happens something amazing, okay? So if you go at second order and you compute the equation of motion for second order gravitational waves, you realize that there is on the right-hand side, there is a source that is made by linear scalar, okay? So I didn't add any extra field, it's just GR at second order. So I compute the equation of motion for my second order gravitational waves. And I realized that on the right-hand side, okay, I have a combination of scalars, okay, and the combination is dictated by the fact that this guy on the left-hand side is a tensor, okay? I build all the combination that I can have. So, and it's also curious to see that on the right-hand side appears also the equation of state parameters. So this guy on the right-hand side feels also if they are in matter, radiation, so on and so forth, okay? So, and what GR is telling me is that if I go at second order, tensors are sourced by linear scalar, okay? I don't need to add any extra ingredient. Okay, now I'm sure that you want to know how big this is, okay? How this contribution is, because these are second order, and then you can think, okay, come on, second order is smaller than linear order. Don't waste time to tell us these things, okay? Let's be patient and let's do the calculation that could be the exercise of this afternoon, okay? Because I gave this exercise in the last school. You move in Fourier space and you compute your equation of motion, and you have your source term in Fourier space on the right-hand side, okay? So since these are product of scalar fluctuation, okay, you know that when you go in Fourier space, this becomes convolution, okay? So come on, let's compute convolution. So we compute convolution and then we have this kernel function here, okay? This kernel function will be a strange combination of the momenta, of the internal momenta of this integral here, okay? But okay, I can do that. So I do that, and you notice that this source function, as is typically called in this community, is proportional to the product of two curvature fluctuation, okay? So remember, okay, that this curvature fluctuation, so this Z here is proportional to phi, of course, that is proportional to my delta T over T, okay? So keep in mind this. This is the curvature fluctuation defined during inflation. Okay, so in this long calculation, I have defined this quantity F that I was telling you is a combination of the internal momenta, and I introduce some function called T here that are the transfer function, because again, so I will do a plot there, a plot later, but the situation now is the following, okay? So it's slightly different than before, because now, okay, I'm computing guy that re-enter within the horizon. Then again, so I need to propagate this guy when they re-enter within the horizon, okay? Let's do this calculation, okay? I define this projection factor, okay? Nothing complicated, just takes into account that we are having tensor contraction between polarization tensor, okay? So then now you have everything, okay? You can solve this equation. Let's solve it. So you use the green function again, you solve the homogeneous and then the particular solution, and then you will find that, again, this will be the solution for this equation, okay, for the tensor fluctuation. Okay, I have the solution, great. So let's compute the power spectrum, because it's the quantity that I want to compute. So I compute the power spectrum of the tensor fluctuation and see what happens. This becomes, so you just take the 2-point correlation function of this, okay, quantity here, that becomes the 4-point correlation function of the scalar, right? Because each H brings with him or with her two scalar fluctuation. So then if I compute the 2-point correlation function of two tensor, this will be the 4-point correlation function of the scalars, okay? And as I was telling you, this phi is related to zeta and also feels the effects of the equation of state parameters, okay? Okay, great. So I know how to treat 4-point correlation function because I learned in my theoretical physics course. So I do the weak contraction, and I realize that here only the disconnected part of the trispectrum, that is this guy here, survives. Okay. So great. Then I am able to build my power spectrum, and I realize that the power spectrum of the tensors is sourced by 2 power spectrum of the scalar. Okay, then you can tell me, then why you insist? Because we have measured these guys. This is 10 to minus 9, this is 10 to minus 9. So this is very small. Okay, don't waste time. I want to still convince you that this can work, okay? Okay, while rewriting my tensor power spectrum, I see that there are some strange combinations that people have computed in the past. You can do it analytically or numerically, okay? But at the end of the day, what I want to know is the amplitudes of my stochastic background generated by this linear perturbation, okay? So again, we are in radiation domination because we are interested on these scales. We have the transfer function here, and then we have the primordial power spectrum, okay? Where you see the bar, okay, these are quantities that have been averaged over time because they are quite oscillating functions, so we typically average over time. Okay, great. So this is the final form of the spectral energy density for this signal, okay? This is today, and this is when it's has been produced, okay, at the beginning of radiation domination. And then again, as before, so we see that these guys feels the presence of extra degrees of freedom of the standard model, okay? Okay, let's do an estimate now. So we have 10 to minus 5 from the amount of radiation, okay? Then I have a 10 to minus 1 that comes from this term here, okay? This is easy to compute. Then I have 2 times the power spectrum of the scalar fluctuation because I've seen that this guy here, so it's proportional to, sorry, here, is proportional to this, okay? That is proportional to the square of the scalar power spectrum. And you see, 10 to minus 5 times 10 to minus 1, 10 to minus 18 from Planck, okay? This comes from the 10 to minus 9 amplitudes of the scalar power spectrum, okay? This AS, that is around 10 to minus 9 at CMB scale, okay? K equals 0.02 inverse megaparsec, okay? Okay, we have everything. Then the amplitude is very small. It's 10 to minus 24. Okay, another unuseful source, okay? Is this undetectable? I would say so, right? So the typical sensitivity of detectors is around 10 to minus 12, 10 to minus 13, 10 to minus 14. So we have something that is 10 order of magnitude smaller, okay? So then this cannot work, right? But do you have idea in mind how this mechanism can work? Who knows? Is the end. Nobody know? So we are. So we don't. So we have computed another very small spectrum. Okay. So we have changed model. We have to change model. No, in reality, the situation is the following. Okay. So what I put in my estimate, okay, is the amplitudes of my scalar power spectrum at CMB scales, right? So this is a plot where I have the constraint on the scalar power spectrum at different scales, okay? So, you know, we are very well constrained by CMB measurement. The most precise measurement about early universe come from CMB. And you see we have very small, how to say, allowed region for the spectrum, okay? If you compute the error on this, is extremely small, okay? So you see the power spectrum on these scales is 10 to minus 9. But you see, if I moved from CMB scale down to mu distortion scales or interferometer scales, the ones that I was mentioning this morning, so you see, there is a huge part where the spectrum is unconstrained, right? So in this part, you see, you don't have any constraint. You have some constraint from futuristic constraint from Pixie, okay? That is emission from mu distortion. You have some constraint from FIDAS, actual one. But then here you are quite free, okay? Okay, then what happens? What happens is the following, right? If I move away from CMB scale, okay, my power spectrum, the scalar one, can increase, right? Who forbids me to have a larger power spectrum of the scalar, okay? So then this means that I can increase my power spectrum moving away from CMB, okay? And I can recompute the quantity that the spectral energy from scalar-induced gravitational waves using a larger amplitude from my scalar, okay? So the only constraints that come from, let's say, actual detector, okay, is P of Z of order 10 to minus 2, 10 to minus 3, okay? So, okay, then let's take, this quantity, okay? Let's take the power spectrum of Z, 10 to minus 2, and let's compute again the amplitude. We compute the amplitude spectral density, and we have 10 to minus 5, the same calculation as before, times 10 to minus 1. Now we have 10 to minus 4, 2 times 10 to minus 2, okay? And this is 10 to minus 10, okay? So we got a larger amplitudes of the signal, okay? That you see here in this orange line. I call it PBH, it will be clear soon, that becomes very large, okay? So I just change the power spectrum because I have the freedom going away from CMB scales, increasing it, and the signal becomes detectable for LISA or even for PTA or for ground-based detectors. So then the question is, okay, beautiful, you have put only number, okay? So how to realize this in reality, okay? People have worked a lot on this, trying to find models to accommodate this extra increasing of the scalar power spectrum. And one of the most common models to realize this is taking a simplistic, the usual model of inflation, okay, with a standard kinetic term and with the potential, okay? Instead of having a monotonic potential, like the one that I showed you before this morning, okay, the famous Slorov potential, okay, here we have something slightly different that at some point has a small plateau, what is called an inflection point that I put, if you want, by hand, okay? I force this potential that is an ultra-Slorov potential, okay, to have an inflection point. I just change a bit the physics of this potential. And you see what happens. So if my potential changes, okay, slightly like this, okay, you would have that the velocity of the inflaton would decrease, right? So you have a kind of inflection point. So the rolling inflaton would decrease, okay, would decrease its velocity. Phi dot is smaller. So I didn't compute exactly, but if you compute the power spectrum of the curvature fluctuation, instead of putting the Slorov parameter, you put the velocity of the inflaton, you realize that it's inversely proportional to the square of the velocity of the inflaton. What this means? This means that if this guy is smaller, then the P of Z is larger, okay? So, and you see, the P of Z is greatly amplified at small scales, okay? Just reducing for a while the velocity of the inflaton. But it's important to keep in mind that when I am at CMB scales, on the largest scales, I still have to recover my CMB bounds, okay? I cannot forget this constraint here because these are real data constraints, okay? Great, wonderful. So I have realized that my spectrum has these features, okay? This is the expected spectrum for scalar-induced gravitational waves, okay? The Gaussian contribution, okay? And it will be clear soon. And you see that has a very peculiar shape, okay? So that is well different from the ones that we have seen before, okay? So we can eventually disentangle this from the previous one. Okay, very good. So I'm adding in my plot different signal. I have the axion inflation signal, then I have this signal from scalar induced, and then I have my vacuum contribution. Okay, then what we have done, we have tried to parameterize this signal, okay? And we have seen that depending on the input power spectrum, we can have different shapes, okay? And then again, we have run, you see, different parameters of the model change different features of the spectrum. But as before, we have run a Bayesian analysis. And what we have realized is that, you see, LISA, for instance, can constrain very important parameters of these models. Of course, we go beyond two simple parameter models. So here we see that we have something like 5 parameters, okay? So besides the number that are not important, I want to highlight what I can learn from this Bayesian analysis, okay? That is something that you will do tomorrow, okay? So I can constrain the amplitudes of the power spectrum, okay? And this is telling me something very relevant because as we will clear soon, the amplitudes of this signal is related to abundance of primordial black holes, okay? Don't be worried. I will clarify soon what these guys are, But remember that if I constrain the amplitudes here, I'm constraining the amount of PBH that I have with Lisa. So then I have the frequency of the turn in the signal here, okay? So this is telling me when my potential is essentially changing its slope, okay? The second slow roll stage, okay? This means that if I measure the frequency of the change of the turn of the spectrum, I'm learning how it is my potential, okay? So if I measure the infrared spectral index, okay, this is related to the spectral index of the scalar power spectrum, another interesting properties, okay? And then if the other parameters, again, are related to physics for this kind of model. So you see, again, so interferometers can teach us a lot about early universe physics, okay? So, any question? So, are you... So in principle, so for the moment, we have seen only the scalar-induced gravitational waves, okay? These do not affect anything about the structure formation. Something different happens here, okay? Because let's look what happens. So I told you that in order to realize this model, okay, so I need something that is of order 10 to z equal to 10 to minus 1, okay? Because I want something, I want then the power spectrum of z of order 10 to minus 2, okay? So then, since this is the square, okay? So people in the 80s have realized that if you have a so large curvature fluctuation, this curvature fluctuation is related to the energy density, okay? Delta rho over rho. Okay? So if you have so large energy density when these modes re-enter the horizon, okay? Just a second. So if you have these modes are here, so they re-enter. So here there are these fluctuation, okay, this z around, okay. So if this delta rho over rho is larger, what is called a critical density, okay, this fluctuation can give rise to primordial black holes. Okay? So these are black holes that are formed in the early stages of the universe, in particular during radiation domination. Okay? So, and again, this guy today are well studied, even even more after the LIGO-Virgo detection of gravitational waves, because they have very interesting properties that are different from astrophysical black holes, and it will be clarified soon. Essentially, you have this fluctuation. So this fluctuation at some point re-enter the horizon. If they are large enough, they collapse in the usual way, and they form a black holes. In this case, so we have a primordial black holes, okay? So the picture is the following. I have my super horizon fluctuation, okay, larger than the horizon. Then after inflation, the Hubble horizon increase again, okay? This fluctuation here goes sub-horizon, okay? And if they are larger than this typical delta C, that is the critical density, they form these primordial black holes. So, and the mass of these primordial black holes, you see here, is related to the horizon at that time, okay? So, wonderful. What this means, okay? So, this means that at the same time, okay, if you want, I have two nice properties, okay? On one side, I have the scalar-induced gravitational waves. On the other side, I have the primordial black holes, okay? That still this guy evolve and merge, okay? And people today are looking to them both in the resolved cases, but also in the stochastic background. So, but keep in mind that we have two complementary information from primordial black holes and from scalar-induced gravitational waves, okay? Remember that here we are talking about quantities that are second-order quantities. So And it's wonderful what happens at the LISA scale, okay? Because people have studied this FPBH. FPBH, okay? I don't know if I define somewhere. FPBH is the energy density in PBH over the total energy density in matter or in dark matter, if you want, represent the percentage of PBH that can account for the dark matter, okay? Because this PBH, after the LIGO-Virgo detection, has been proposed as one of the main candidates for dark matter candidate, together with other things, okay? So from different effects, from gamma rays, from CMB measurement, from gravitational waves measurement, there are already strong constraints, okay, on the amount, on the fraction of PBH, you see? And it's curious to see that from, let's say, masses, in this range of masses from 10 to, for masses larger than 10 to minus 9 solar masses, the situation is already, let's say, saying that the fraction is very small. You see 10 to minus 2, 10 to minus 3, but there is a window, okay, where this is unconstrained. So in this window, that is around 10 to minus 13, 10 to minus 12, so PBH could be the total amount of dark matter. And see what happens. So I told you that there are PBH on one side and there are scalar induced on the other side. So you are smart and you are able to compute the frequency that is corresponding to this, through this relation to 10 to minus 12 solar masses. So you do the calculation and you realize that the frequency corresponding to this 10 to minus 12 solar masses is 10 to minus 3 Hertz. So Jessica told you that millihertz frequency band is the regime of space-based detectors. And in fact, you see LISA, okay, one of the main candidate gravitational waves detector in space, has the possibility to detect these scalar-induced gravitational waves at the same time constrain the dark matter, okay? When I was discussing this morning about dark matter with gravitational waves, this is one clear and beautiful example, okay? So scalar-induced gravitational waves are sources of gravitational waves, but are also generating primordial black holes, and these primordial black holes can give rise to, be the responsible for the dark matter. It's very small masses. Okay, it's taking this part here. Okay? This is the only window that is still almost free. Okay? This is probably not the most updated. There are also some other bound, but still on the other scales. But still on the 10 to minus 12 solar masses, this is still free. Okay, great. So these scalar-induced gravitational waves, okay, this is a bit more technical, okay? Please stop me if you think that is too technical, okay? But we have seen that, roughly speaking, okay, every h is proportional to z, okay, to curvature fluctuation, okay? So then we realize, okay, no, other people realize, then we study more in details, okay, that of course, being h proportional to the product of 2z, so this gravitational wave signal would be very non-Gaussian, okay, because if you compute non-Gaussianity here, being the product of two Gaussian, even Gaussian field, this would have a chi-square distribution, okay? So we expect that then these guys are sensible to non-Gaussianity, okay? For people that are less familiar, non-Gaussianity, okay, is essentially the Fourier transform, is the amplitudes of the bispectrum, that is the Fourier transform of the 3-point correlation function, okay? So non-Gaussianity is important for mainly two reasons, okay? It gives to us the level of interaction of the field in the early universe, okay? More the fields interact, larger non-Gaussianity would be. And on the other hand, is a powerful discriminator of inflationary model. So at the same time as we have seen NSR this morning, the 2D plot of the CMB, also FNL, that represents the amplitudes of non-Gaussianity, okay, allow us to distinguish the single field model from multi-field model and so on and so forth, okay? So, and we realize that if we take the most famous shape of non-Gaussianity, that is the local shape, where you have a Gaussian field here plus FNL times the square of a Gaussian field that would be non-Gaussian by definition, okay? You plug in your spectral energy density and you get something that is the Gaussian contribution, right? Plus a term that is proportional to FNL squared plus a term that would be proportional to FNL to the 4, okay? What this means? So this means that these terms, these non-Gaussian terms, contribute to the spectrum. And you see that if you add this term, okay, we did it last year, so the spectral shape changes, okay, in different ways for different level of FNL, okay? And this means that, in principle, LISA, in this case we did for LISA, where you see the yellow line is the LISA sensitivity, is sensitive to non-Gaussian features in the primordial perturbation, okay? So then why not running a Fisher analysis? We run this Fisher analysis and we estimate the level with which LISA can constrain non-Gaussianity. And it's amazing to see that LISA have the possibility to constrain non-Gaussianity at the percent level, okay? So this was something that, of course, is another interesting application of interferometers. So later, we refined this analysis in the LISA cosmology working group, okay? With the Monte Carlo Markov chain analysis, okay? This time, together, we put all the signal parameters, okay? The noise parameters of the detectors, and we added also an extra complication that are the foregrounds, okay? And again, this analysis that we did last year, okay, confirmed that we can constrain with LISA FNL at order 10 to minus 2, okay? So, and again, other interesting tests of the fundamental physics and early universe. Okay, good. Question about this new mechanism? Too clear, too fast? Less, not clear at all? Yes, okay. It was done by the in the collaboration papers, okay, both Nanograv Nanograv APTA, PPTA, and Chinese pulsar timing array. They didn't do the analysis, but we did independently because at that time we were not part of PTA, okay, and we put the constraint on FNL, okay. We add the non-Gaussian contribution through in PTA data, and we try to infer FNL from PTA data. Yes, we did. Sorry? The results is again that, so the fact that this guy here, contrarily to CMB, okay, in CMB analysis, it's very curious, okay? This is something that we are still investigating. So you see, in CMB analysis, when you do, for instance, the bispectrum analysis, okay, FNL enters at linear level, okay? Here it enters at quadratic level, okay? It seems to give stronger constraint, okay? And also for PTA, we obtain something constraints that are compatible or comparable at the level of precision with the CMB, because, you know, with CMB, you have FNL in the local shape is something like 0.3 plus or minus 5, something like that. Okay, is compatible with 0. Okay, so we get something at the level that is more stringent than CMB analysis. Okay, with PTA. In fact, we did this analysis. We compute the bias factor, and for us this was one of the preferred model even against supermassive black holes. Okay, please. Okay, very good question. Okay, so the answer, okay, is the following. So these guys are formed here. This is the end of inflation. These guys are formed here. So you don't, okay, first of all, you would expect that having formed in the early universe, you would expect these guys to be at very high redshift. So we don't expect to have PBH very close to us, okay? Instead, we expect that this would be a redshift like 30 if you want, right? So you don't expect to see, or it's better to invert. We don't expect to see astrophysical black hole at so high redshift. So if we see something at very high redshift, even above 10, I'm too pessimistic here, okay? So this would be an indication of primordial black holes. On the other hand, I would expect that these guys are spinning, right? So these guys, so the formation mechanism for these guys, so I don't think that it would be expected that they are spinning. So if we find something that is not spinning, that is another indication. Then the other point that probably is addressed in not very well, but the mass of this PBH, it should be very small, okay? Is a very small mass, okay? We don't expect to see something, the survivor thing is asteroidal stuff, okay? So we expect to see something very small. If we find something with the subsolar mass in the data, this could be an indication. Other question? Come on, let's start the discussion. So you like more the axion inflation case or the scalar induced case? Who likes more the scalar induced? Okay, I didn't tell you some things for which I like more the scalar induced, okay? This guy here is the only background that is there for sure, okay? While all the other stuff, I change a bit, I tune a bit, this is GR, okay? If in the future, you will build your own detector that will have a sensitivity of 10 to minus 24, you get the Nobel Prize, okay? Because this background is there, right? Because we have measured the scalar fluctuation, these are CMB measurement, okay? Assuming that they are scale invariant, I don't do any modification at any scale, this is the only guy that is there, okay? While you can talk about, for 10 days, about axion, phase transition, cosmic strings, so this guy here is guaranteed, okay? This guy, okay, is in the data, okay? Now you have to develop more sensitive detector to go down at the level of 10 to minus 24, okay? But for sure, this guy is in the data, okay? I have been too pessimistic here. Okay? It's the unique guaranteed background that we are sure that is there, okay? Other question, sorry. Okay, still in the limit. If they are very small, yes, they should evaporate. So this will be in the left part of the spectrum. That's true. So what I show here are still window where my black holes have not evaporated yet. This is a window where still black holes can exist. Other questions, please. Left and right. No, it's more simple than that. So the fact that so we have amplified only one gauge field, okay, translate in the fact that the left and right polarization of the tensors, okay, have different amplitudes. Okay, so you don't need to invoke any chiral anomaly here. So it's more simple than that. Please. What do you mean? Okay, that's a good question. I think that if you imagine that, I don't know if I can give you the best answer, okay? But if you imagine that, for instance, this PBH could be the seeds, okay, for some supermassive black holes, right? For instance, this PBH cluster can cluster in the inner part, okay? And this, for instance, could be a way to be dark matter, for instance, that give rise, for instance, to supermassive black holes, for instance, okay? I don't know if I reply to your answer, but the mechanism is, okay, you have this object in the universe, okay? On one side, you treat them, you look for the mergers and you look for the signal. On the other side, they are candidate for dark matter. Yes, for instance, yes. Yeah. Other questions? Okay, if there are no questions, let's move to the final source of the early universe that I will discuss, that are first order phase transition. There was also some question this morning. I don't know if Tanya discussed, because I was a bit late in his lecture. Did Tanya discuss phase transition in detail? Okay, sorry, I missed that part. Okay, let's see if we don't overlap too much. Okay, so you know, as I explained, so the universe expands. Okay, and this means that particles can go out of equilibrium. Okay, so so if the temperature goes down, there can be many phase transition. Okay, the most famous are the electroweak or the QCD phase transition. Okay, in the standard model. But what happens if we go beyond the standard model? So the typical definition that we have, and the simplest definition that I can give you for a first order phase transition, is a transition in which there is a discontinuity in the first derivative of the Gibbs energy. Okay, so you compute the free energy, the Gibbs free energy, and this is typically given by the energy, the internal energy, plus the pressure times the volume times the temperature times the entropy. Okay. So you compute this function, you look for discontinuity, and if you see that if these quantities are not continuous, okay, this gives rise to a first order phase transition. Why I'm talking about first order phase transition is related to something that you mentioned in the morning. That is the fact that if you compute the phase transition in the standard model, the electroweak one. So this is a crossover, as you were telling this morning. But what happens if we go beyond the standard model? And I will show you how to go beyond the standard model. Okay? But more in details, okay, let me try to introduce, in general, a phase transition. Okay? So we change a bit the mechanism, okay? Because before we were not talking about causal mechanisms. These are mechanisms that happens sub-horizon, okay? We have seen before, right? Okay, that inflation happens here. So inflation ends here, okay? Then for primordial gravitational waves, I compute here and then I propagate. For scalar-induced gravitational waves, it's true that this comes from sub-horizon mechanism, but again, also here, I have sub-horizon formation of bubbles, as we will see. These are causal sources, so they cannot operate beyond the horizon. So if I want to keep mathematically this relation, then I relate my wave number or frequency to the Hubble horizon that is related to the temperature, and the parameter epsilon that is related to the source of the phase transition. Okay, this is a parameter that I keep less or equal than 1. Okay, so since this is a causal sources, okay, this quantity here is essentially the redshift. Okay, A star, that is the scale factor at the formation, over A0, that is the scale factor today. Okay, and then I relate the emission frequency at today with the emission time. Okay, with the frequency at the emission time. And this is a simple relation because I know this guy is in the lambda cold dark matter model. We have seen also this morning. So if you relate these two, you find that there is a simple relation between frequency, it's written here, and the temperature. Okay? So look what happens here. So if I have a T star, a temperature of emission of 1 TeV, and you plug here, you realize that this guy, and you have epsilon 10 to minus 2, later we will see what epsilon is, so you get a frequency of today of the millihertz. So again, you see that we are in the Lisa band, okay? Wonderful. Millihertz frequency band, space-based detectors have the possibility to test first-order phase transition. Okay? So this epsilon here, as I was saying, is the dynamics of the source. Okay? It will be clear soon. So in this 1 TeV corresponds to the electroweak scale. So, of course, you can extend this relation, and you can realize that each frequency is related to a temperature, okay? And you go from QCD phase transition at these PTA scales. So PTA is telling us that if the gravitational wave signal is from phase transition, then a QCD phase transition has happened in the early universe down to the electroweak scales that Lisa can tell us. And here again, to some other scales, temperature related to LVK analysis, okay? So, and you see, so this relation between frequency and temperature, okay? But how a phase transition works, okay? So, universe expands, fortunately, the temperature decreases, okay? And we can trigger this phase transition. What happens is the following. So we have an effective potential, okay, at high temperature that has two minima. So it has a false vacuum here, okay, and then I have a true vacuum here. So the point is that as the temperature decreases, okay, my X field, if you want, pass from the true vacuum down to the false vacuum, okay. It goes here through tunneling, okay. So because this false vacuum here has become unstable, okay? And for this reason, there are some thermal or quantum fluctuation that can nucleate bubble of the true vacuum. So my X fields can move from here to here. So you see, I go from the true vacuum here, and then I go I go from the false vacuum in the true vacuum here. Okay. So the point is that these bubbles here can grow. Okay. You see here they grow here, going from here to here, and they can match each other, okay? They can grow each other, okay? And you see, when this bubble collide, this bubble collide, so they can generate gravitational waves, okay? So this means that the nucleation of bubbles of the true vacuum can give rise to gravitational waves. And a necessary condition is to generate a large gravitational wave signal is to have first order phase transition, okay? So what are the three main mechanisms? So one mechanism is the colliding of the bubble themselves, okay? People have realized that then the plasma that is around, okay, can also experience shocks, okay? And these shocks will also form gravitational waves, and then also sound waves in the propagation, okay, of the bubble can generate also gravitational waves. So as we will see soon, the total signal will be mainly the sum of these three contributions, okay? I tell this and then I take your question, okay? Again, the situation is similar to the one before. So you have the gravitational waves on the left-hand side, and then you have an isotropic stress on the right-hand side. Again, my anisotropic stress is given mainly by collision, sound waves and turbulence in the fluid, and the magnetic hydrodynamic turbulence. So if you work in the field, so you know that mathematically this is given by this equation here, okay? But the main message is that the total contribution is the sum of the three. And in these papers, and also in the Lisa Red book, you can find more details about these three mechanisms. Please. Mm-hmm. So you're asking what happens if this guy has a mass? I think that all of these, the sound waves is still the bubble expansion, okay? That is the coherent motion of the bubbles, okay? That has a sort of feedback in the plasma, and then these guys in these sound waves propagate in the plasma. Yes. Yes. So I think that I have here, let me give you more details of people have or not. I don't have. No, I don't have. Okay, I will tell you, I will give you later slides where there are a list of all the references where they compute analytically or numerically this spectrum. Okay? So if you translate this in spectral shape, you see that here I let correspond the blue, that is the bubble, to this shape of the spectrum, okay? The green to the sound waves contribution, okay? and then the magnetic hydrodynamic turbulence contribution to the red one, okay? So in principle, you could distinguish all the three. In general, what people do is to sum up all of them, okay? And you see that the black one is the total contribution, okay? And you see again that we are at the TV scales, we are right in the middle of the LISA frequency band. Don't get confused by different colors, because this was a study that we did for different LISA sensitivity. The main message is that gravitational waves from phase transition can be detected by LISA, and we can detect also if they would be there, if there is a first order phase transition. So before telling you when I can have a first order phase transition, let me tell you with these parameters that probably you are curious. Okay, so the parameters that enters in the estimation of the signal are the duration of the phase transition that is given by the inverse of this parameter beta, and the speed of the bubble waves, okay, of the bubble walls. So I can combine these two, and I can define the size of the bubbles at the collision, okay? So everything is related to these two parameters, h star over beta and h star times r star, okay? And this is telling me what is this parameter epsilon that is related to the bubble collision, okay, and to the sound waves and the magnetic hydrodynamic turbulence. So my epsilon here will be these two quantity, okay, for this mechanism. So this means that if I compute, if I want to compute my spectrum, again, I assume that I am in radiation domination. I have this quantity that is given, that gives us the duration of the phase transition, okay, with respect to the Hubble time. And then I have this quantity here that keeps into account the amount of energy that I have compared to the total energy, okay, that I can rewrite in this form here. And you see that this would be the general form of the spectrum, okay? And you see that it depends from simple four parameters, okay? Temperature of the phase transition, the inverse duration, the strength of the phase transition, and the bubble wall speed, okay? So the study of the phase transition is not as simple as I told you, okay? It involves strongly analytical and numerical computation, okay? There are groups in Spain or in Portugal. There are groups in Helsinki that are very expert on simulation of phase transition. I'm sorry that I didn't report the full list of, I will add in the slide that we will put online, of people that contribute to this field, okay? So there was a question this morning about, okay, how I go beyond the standard model. So these are simple models, okay, beyond the standard model that can be tested, that can give rise to a first order phase transition with physics beyond the standard model, okay? So for instance, we did these studies in LISA. So direct extension of the minimal supersymmetric standard model, okay, has been studied 10 years ago, okay? Or you can directly couple the X with some scalars, okay? This is other physics beyond standard model. Or you can work in 6 dimension or in more than 4 dimension, okay? And you have 6 operator here. Or you can also couple the standard model with some dark sector, okay? And also in this case, you can have generation of first order phase transition and the generation of gravitational waves. And then, of course, you have other models. This is not exhaustive, okay? There could be other models, but you see, there are models beyond the standard models to generate a first order phase transition, okay? So, and when I was telling you at the beginning this morning that we're testing high energy physics, this is one of the most clear examples that I like to mention to people, because we have tested, as you have seen with this simple example, some physics that cannot be tested with colliders, okay? And you see what happens. This is the only more details examples that I show. This is a nice exercise that have been appreciated also by particle physics, okay? Because we studied this simplest extension of the standard model, where we added a singlet to the X field, okay? This is the potential plus a singlet scalar field, okay? This is the potential, okay? If you study the dynamics of this model, you find that the signal is this one, okay? Sorry, is this one. This is because, sorry, I skipped before. Let me go back. The typical shape of a model from phase transition is a broken power law. Okay, you see that you have a tilt here that is typically settled by causality. Okay, because this is a causal source. Okay, this will be always f to the 4. Okay, this is or f to the 3 or f to the 4. Okay, and then you have a small plateau here, and then you have another power law here. The typical shape for phase transition is always a broken power law. Okay, this is another difference between with respect to the other models. Or you have more complicated phase transition where you have a double broken power law. And you see here you have the different contribution. Sorry if I go back and forth. So you see that the model here is again a broken power law. Okay, it looks that is slightly smaller than the LISA sensitivity, because here I'm showing the sensitivity and not the power law sensitivity. But the main message is the following. So if you look at this plot or this plot here, okay, you realize that we constrain the parameter space of the model, okay, that is absolutely complementary. This line here comes from some constraints that comes from FCC, Future Circular Collider, or high luminosity HLC, okay? And you see that LISA can probe the parameter space in a complementary way with respect to collider, okay? This is a very nice exercise that we did, okay? And I think that is extremely interesting because you realize that really gravitational waves detector and particle physics detector are absolutely complementary. And you see, you can test BSM scenarios with a joint detection of LISA and FCC or LHC, okay? I should stop here, right? Just a second and then I come. So when is supposed to, I have 10 minutes? Okay, great. So I will not discuss in details, but there is another extra source of gravitational waves that is well studied in the context of interferometers, that are cosmic strings, okay? Cosmic strings are left over of a phase transition, okay? When Tanya was mentioning this G mu, this is the string tension, okay, of the cosmic strings, okay, and then a network of cosmic strings, okay, can generate a gravitational wave background, okay. This will be cosmic strings. You see that the spectrum changes, okay, for different value of the string tension, okay, and you see again that LISA, for instance, in this case, can constrain for different value the string tension. That would be important information on the nature of the phase transition. Please, sorry if... Because, so here you are looking through gravitational waves, right? In the other case, you are looking through particle interaction. Gravitational. Yeah. 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 That's a very nice question. Other questions? The last line are more silent. Why? So I would stop here, okay, and take your question. Or if you want, I can tell you how to test the cosmological principle with gravitational waves. As you prefer. Question. First question. Then if there is time, we will do that. So to be honest, I didn't put because there was no time. Typically in the school, I do also this part in details, but these are related to there are models related to strings. This one. Why do I have a? Okay, the infrared is causal reason. Okay, all the infrared you see goes more or less with the same slope. Okay, here is mainly related to the duration of the phase transition. Okay, and you see that this parameter here. Okay, there is this the part of the string size of the bubble. Okay, that sets essentially the peak of the phase transition, and then you have this other behavior here that is a different power law. Okay, from here you cannot really understand. Okay, let me see if I found something more clear. Okay, here you see that you have this probably from here. So you have the sound waves that is telling us this part here, and then you have the magnetic hydrodynamic turbulence in this part here that is contributing mainly in this part. So this is the sum of these three different contributions. Of course, the peak is related to the duration and to the dimension of the bubbles. Yes, and in fact, yes, yes. I don't know. I never work on simulation, so. But if they don't collide, wouldn't expect any signature here. Right? Other questions? Okay. If I have other 5 minutes and you are curious, okay, let me tell you why I can use gravitational waves. This is something that it's not very well in the sense that it's not studied a lot, but I think it's extremely fascinating. Okay, and when Tanya was mentioning this morning, so I am one of the first presenting the formalism for the anisotropies of the stochastic background for the cosmological case. Okay, so then people has realized before for the astrophysical case, but all the framework for the cosmological one, I think that I was one of the first developing that. So look at here, right? So you are here, okay? Hopefully not in the space, but in this room, okay? And then you have your gravitational waves decouple at the early universe that they propagate. Okay? As we have seen this morning, they leave the imprinting on the CMB, they leave the imprinting on the large-scale structure, I didn't discuss, and they leave imprints on smaller galaxies, okay? And then we look through here with the T or with LIS or with LBK. So while these gravitational waves are propagating, okay, so they will inherit a spatial dependence that is something that is hidden in this direction dependence here. Of course, so this is a perturbative expansion, so I don't expect that this is large, not for a cosmological nor for astrophysical background. So the description of these gravitational waves is a bit tricky because I have, again, my background, okay, where for my background I have my phi, psi gravitational potential, and on top of this I have my gravitational waves, Hij, and the assumption that we do is that these gravitational waves of high frequency, this one, you see that they have high frequency, propagate through the low frequency potential. You see this is related to this, okay? So it's like is the regime, the so-called geometric optics regime, okay? Where I can treat these gravitational waves as particles, okay? Moving on a geodesics. So if you compute the contribution from these gravitational waves and isotropies, okay, you have mainly two mechanisms, at the production and during the propagation. So the reason why for astrophysical background the contribution is larger is that the production when the source is in the galaxy, if you want, it has a larger contribution, but we will see soon. On the other hand, you can imagine that if this propagates on these potential that are also varying in time, okay, and they're also propagating in an expanding universe, okay, so this will be redshifted, okay. So let's look what happens. So since we are in the geometric optics limit, you can study these guys with so-called Boltzmann equation, okay. So you do the calculation. I don't want to annoy you with this, okay. And what you realize is that this gravitational waves anisotropy has three mainly contributions, okay? One is given by the initial production, and one is given by the propagation through the large-scale structure. So then, okay, so you decompose your gravitational waves anisotropies in multiple space, you compute the angular spectrum, and you see that this is given by three contributions, okay? So without losing time, okay, as photons, also gravitational waves experience the Sachs-Wolf, that is due to the fact that the gravitational waves, that these potential are redshifted, and also the integrated Sachs-Wolf, that is due to the fact that this guy is varying in time, okay? So this means that gravitational waves, similarly to photons, are new probes of large-scale anisotropies. And the physics is very simple. So you have this gravitational wave that is propagating, so you have some redshift effect here, and some integrated Sachs-Wolf effect here, okay? So we develop a branch of class that is the main code to the Boltzmann solver code together with Julien, Lesgourg, okay? And we computed the expected background for, the expected angular spectrum for gravitational wave background, okay? And you see here that compared to CMB, okay, the spectrum for cosmological gravitational waves is larger, okay? Okay, and the reason is that I'm integrating for a longer time, okay? And this means that it's not very small compared to the CMB1, okay? But starting from here, we develop something that is particularly beautiful, okay? So both the photons and both the scalar induced, and both the cosmological gravitational waves propagates on the same potential, okay? So they all feel the same geometry of our universe, okay? So, and if we are in GR, okay, and we are in a lambda cold dark matter model, okay, this perturbation has a common origin from inflation. Okay? The fact that these gravitational waves propagate on the same background induce a natural cross-correlation between gravitational waves and galaxies, for instance, and also between gravitational waves and CMB, okay? We realize that there is this natural cross-correlation between gravitational waves and CMB anisotropies. So, without going into the details, okay, of course, this signal is small, okay? You need something like BBO or DISIGO, or you need large amplitudes for the spectrum to get a reasonable SNR. But what I want to emphasize is the following. I can compute the level of correlation between these two messengers, okay? And I see that on large scales, small l, these are highly correlated because essentially they travel through the same universe, okay? So you see that the correlation is very high. So then let's look at here. So you take your CMB map, okay? You take Planck's Mika map, okay? What you do, you build your conditional probability of your map of the gravitational waves, because the seeds is the same, okay? Is the probability of the distribution of the gravitational waves given the distribution of the CMB, okay? That I know. So this means that since the seeds are the same, I can reconstruct it what are called constraint realization, okay? This is a picture of what I expect from the cosmological background when I will measure, because I already know the distribution of the CMB, okay? If the detectors will be high-resolution detectors, you will find a map like this, okay? This is the noiseless case. You see that is as beautiful as the CMB maps, and you see the same level of details, and you have built a map with its mean and its covariance, okay? Unfortunately, we have a big limitation with interferometers, that is the resolution, okay? Interferometers, all interferometers, roughly speaking, okay, has a limited resolution that is translated in L, that is something like smaller than 30, okay? Even if you combine a T plus 2 cosmic explorer, you would go to something like L100, but this is very optimistic, but typically L10, I would say that is a reasonable resolution for interferometers. So this means that you have to convolve your map with the resolution, with the noise of your detector, and you see that here you are losing some fine details. But you can still use this constraint realization because you know that in the CMB, we have measured some hemispherical power asymmetry. Okay? So we know that on the largest scales, L2 equal to 2 or 3, we have measured that this hemispherical power asymmetry. So in principle, I give a model to try to model this hemispherical power asymmetry, and I build the constraint realization map, and I can see if there will be in the gravitational wave data a distribution that matches with the one expected from CMB, or gives something different, okay? So, and you see here that in this way, so gravitational waves has been a way to test the hemispherical power asymmetry, so our cosmological principle, because this would indicate a violation of homogeneity and isotropies given by these fields, simply with the stochastic background of gravitational waves, okay? And this is a simple application, so the details are a bit too technical, but you see, we have found another interesting way. So there are people that have looked also to the cosmic dipole with gravitational waves, both with resolved sources and with the background. I will not discuss here, so if you are interested, please ask. So I would stop here, sorry, probably I'm late, okay? So we have seen that for the early universe part, okay, gravitational waves offer a very interesting way to probe our first stages of the universe. Several mechanisms can produce a detectable signal at the interferometers, okay? We can probe by energy physics, this is particularly interesting, and also we have seen that gravitational waves can use as a several test for different cosmological aspects. I think that what I told you here, okay, is something that is really, how to say, limited in the sense that there are a lot of other applications that I didn't discuss. I would need more time, but I think that the future is very bright for gravitational waves. People at CERN, they say that this is a golden era for gravitational waves, okay? So, and I think that you will be the main actor for the future in order to shed light on these different aspects, okay? With this, I stop here the early universe part. Tomorrow we will see the late universe part, okay, where I will try to teach you how to infer the cosmological parameters like H0 from the data, okay? And then we will have the exercise in the afternoon. Okay, let's stop here and let's take your questions.